Hello and welcome to last option. In today's video we are going to discuss about the solution of the satellite problem. In satellite problem the basic concept used is simple kinematic equation, and especially that is non-inertial frame, means acceleration is not constant in that case. However, whatsoever be the case, the differential relation between the acceleration, velocity or the distance covered is always same. And one more concept is used, that is the distance between the 2 points in their vector form. So using these two things we have come to the solution of the satellite problem. So let's see how we come to the solution. Let's discuss the solution, and for discussing the solution I will be referring these notes along with the other form, that is one note, in order to get a clear understanding of the solution. So let's consider the question again, and let me reframe it to you. Just for a while, we have a planet which is analogous to Earth, and we have the other planet orbiting around this Earth, and from here we want to launch a satellite so that it gets soft landing to the planet. So for this objective we are using a satellite or a rocket in order to put our satellite into the correct orbit or onto this surface so that we get all the information which we want. And for that launching we are setting it from the planet like Earth, and up to a distance of r, means r is the distance from the center of the Earth, we are using its thruster which is pushing it up, where its velocity is directly proportional to its rate of change of velocity at the time. So we were asked that how much time would it take for my satellite in order to reach from its launching position to its destination. Okay, so for this I need to consider the two conditions. That is, first, when my satellite is in the range of small r, that means up to the threshold distance where I am pushing my thrusters on, and the next would be after it. Okay, so we would be taking two different equations, especially they are same but just two kinds of form, and for that let's suppose when my satellite is in the range of small r, in that case I would write the velocity equation plus acceleration equation, and with the help of those I will get the distance equation for my satellite, means how much distance it is covering with respect to time. Okay, so let's take about the velocity. For the velocity we were given that v is directly proportional to dv by dt. dv by dt is nothing but the acceleration of that satellite. So what I can tell is v is equal to k times of dv by dt, and along with it I would get velocity as v equal to v naught e raised to t by k, where v naught is its initial velocity, and sufficiently if you want to consider it's just from the launching position, you would say v naught is 0, but at the present time I won't put it because with that my equation will get terminate off and I will not get the exact relation which I want. So why is that happening is because we are telling that it's directly proportional to its instantaneous velocity, and at t equal to 0 it is equal to 0. So means after t greater than 0 I won't be having any type of velocity which is not correct. So for that consideration we are just taking v naught, and considering that would be small, which we can put into the final equation in order to get the simplified version of it. So with this we are getting v equal to this much. Okay, so this is the velocity with which it is going in this direction, and as soon as it reached the surface of this analogous planet Earth, as it was rotating about its axis with an angular velocity of omega, so naturally this would get this direction which is equal to v equal to omega r. Okay, so with this it would get to the direction. So the question is, while launching the satellite from the Earth, when we observe it we do not get this thing into our intuition. This is basically because we both are sharing the same frame, and that's not an observable quantity. But in this case we are not considering like air drag or anything else, and especially our frame of reference is outside the planet, means all the things which we are observing is from the outside of the planet, and that's why we are considering this pseudo force for us. Okay, so these two velocities will contribute it to path like this, where its path will be in this manner, and for this much a portion we are going to consider. Okay, so velocity can be written in the vector form. I am taking vector form in this because vector form simplifies the complexity of the direction, means you need not to consider what's happening in the I direction or the j direction differently. You can just put them into a single equation. Okay, so this is the velocity equation for s lesser than r. Okay, and for the same thing we can write the acceleration. However, acceleration won't be required much, but I'm taking it. Okay, so this we what we got for the velocity. This we simply tell as acceleration equal to v by k times, where v is its instantaneous velocity, which is nothing but v naught e raised to t by k by k. So this is the magnitude of the acceleration with which our satellite is going to push off to the position. Okay, and it is not having any x direction acceleration. Okay, so let's talk about something about position. Position, as I'm considering the vector form, I must know the initial position plus final position in order to put into my equation to get a clear form. Okay, so suppose I'm launching it from the surface of this, and obviously I would be doing it from the surface. So means its position, that means s of y position at t equal to 0 would be equal to r, and s of x at t equal to 0 is simply 0. Okay, so these two factors to be considered while writing the equation. So for the x direction, as there is no acceleration, I can just write distance equal to speed into time. Speed into time, minus is considered because I'm taking I cap. Okay, and for the y direction, I would use the relation that velocity is nothing but rate of change of distance with time, and with the help of that I would get this equation by considering that s of y at t equal to 0 is equal to r. So this is the position vector of the satellite along the y direction. This is the position vector along x direction. So writing the overall equation for these, I would get as means position vector as these two in combination, where x and y both are considered, means I am just tracking the position of the satellite with the time like this. I am taking these things into consideration, and this is what actually we need. So let's proceed. What next thing that's more important here, as my satellite is going only at a distance of r with these quantities like velocity, acceleration and position, only up to position equal to r, what I will do is I will put my s of t as equal to r in order to find how much time would it take to reach to the position. Okay, so with this I would put in this fashion. I'm taking t1 here only because I'm just considering let time t1 is taken for one path of journey, and next time t2 has been taken to the next path. Okay, so by just taking this modulus of these s of t, I can write this equal to r, and with the help of that I would get the equation for t1, and here I am using the expansion e raised to t by k because I want my equation to be present in the simplified version, and for considering that the e raised to t by k factor is considerably less but not that much, we can come to the equation of time equal to this much by doing just simple mathematics. I can come across this one. So this is the amount of time which my satellite would take in order to reach a distance of r with that conditions. Okay, so I have assumed it as let equal to alpha because I need this factor for the next calculations. Okay, so this was all about the first path of the journey. Now what about the second path, where I am considering my s to be greater than r but lesser than r dash, means in between position of these. Okay, and also considering the orbiting part. And for time greater than alpha, means I have not switched my time equal to 0 again in order to calculate t2. I have just continued from that path. Okay, so writing the velocity equation for that thing again in the same manner, but here I won't be having any acceleration for this. Okay, that is why I have considered this. Note this equation where I have write it as v equal to v naught e raised to alpha by k, where now this whole quantity is constant. Okay, alpha, why I have put that equal to alpha? Because till the alpha time it would have reached to the velocity of this, and after that it will continue with this much of velocity until it reaches to the destination. And omega r is always present. This is minus, I have just noted it in plus, so in order to show magnitude is plus but the direction would be negative only. So that is why I wrote this velocity equation as minus omega r I cap plus this much factor into j cap. This will continue. Now writing the position with the help of this, directly distance equal to speed into time, with that we can come across. Now I need to put this s2, means what is the magnitude of this s2, that should be put equal to the distance which it would cover in between those, like this much. I need to find what is the magnitude of this, that means how much distance it has covered, so that I can use this relation, means the relation of the position vector. By putting that equal, I can get the amount of time it would take. Okay, so by just using the concept of vector analysis, means the vector kind of thing, writing the two position vector for these two, note the position vector clearly, that should be means used very precisely. Okay, I have just taken the consider for here t equal to alpha, and for here t equal to t2, means time it would have taken for that, and that exactly what we need to find is t2, how much t2 is. So by just doing again, just continuing the same pattern, I have come across t2. Obviously it seems like very fuzzy equations, but this is kind of a simple thing. Just you need to know how to solve a quadratic equation. So with that I have got time t2 as this much. So I have considered this as equation 2, and the previous equation which we got for the time as 1, and by equating and by adding those two, we would get the final time. But one more thing which we need to do is considering this v naught, as we have considered it as to be less, but we haven't put in the initial equations, so that we cannot get terminate equations after all. So here we need to think like v naught to be equal to 0, means just approaching to equal to 0. With the help of that I can get my time equation in this fashion, which looks very fancy, isn't it? So this much of time it would take in order to reach to a distance of r with the condition as mentioned. And for time t2 I am getting this much. At first when you see this equation you would get shocked, it's coming lesser than 1 second, means nano, but that's not true, because t2 is equal to this, and it's having also a factor called alpha, where alpha also need to be considered. So time net which I was supposed to calculate is equal to t1 plus t2, and by putting this value of alpha here, what is alpha? Alpha is nothing but t1, means the time it would have taken to reach to this position. So by just doing this simple calculation I can get my time net as this much. So this is the total time which my satellite would take in order to reach to the orbit from the launching position with that condition satisfied. So this was the answer number 1 for the question. But one more question was also mentioned at the last, that is how much distance does my satellite, means which was orbiting around the orbit that we mentioned as L2, I suppose, how much distance would it have covered? So that is simply how it means it would be moving with a constant velocity So distance equal to speed into time. Its speed can be found with the help of balanced force, because it's moving in a circular force. What I can do is mv square upon r should be equal to the gravitational pull between these two planets. And also it was it means it must be taken, means gravitational pull must be considered in between those. So time we know because we got this, and velocity we can find out. So simply we can write the distance it would cover in those time is this much. So let's overview what we discussed. Okay, so what we discussed is, with the help of this concept we can deploy our satellite into an orbit which is having some planet, so that we want our satellite to be caught to this gravitational pull. So whatsoever be the condition, you just need to follow the simple kinematic equations and consider it as xy plane. That would simply divide our problem in the simpler way. It won't affect, because here we are not anti-rotating frame, means the frame is at the rest, so that we need not to worry shifting our origin just to with respect to the velocity. We can simply put it to a static form and write the simple equations, and with the help of the kinematic and the differential equations we can get it easily. So this was all about the satellite problem. It's about fascinating thing, because with this small mathematics we can put our satellite to a desired position and inspire many young minds. Okay, so this was all from my side, so hope you like this. So let's focus on the future, that we get the more interesting questions. That question won't be like mathematics, but it will be like interesting form, like how we can use those simple mathematics in order to desire a long way journey. So thank you for this. Thank you very much.